Hey there, in this video I'm going to be showing you how I built a retrieval-augmented generation application with the help of Hono.js, Couchbase, Nebius AI and Cloudflare. Now, why did I pick Hono.js? So Hono.js is a really lightweight web framework that is optimized for edge and serverless deployments. You can very easily deploy this with the help of Cloudflare workers, Vercel, Edge, or even on Dino or Bun. And the great thing over here is that you still get all of the great features with any modern JavaScript framework out of the box. For example, server-side rendering or TypeScript support that's completely inbuilt. So that is why I wanted to build an application that has a very low bundle size, and Hono is the perfect framework for being able to do so. So you can still have your node-based NPM modules that you might use. For example, in this case, I'm using Couchbase, which historically, like, of course, you cannot directly just inbuild into a React application. You need to have a server. So for example, with Next.js, you can very easily then have that server-like experience, but not need to have a dedicated Node.js server. So that's one of the great things about Hono. Now, apart from that, what the application actually does, so it is a take on Star Wars. So if you are probably trying to find planets in the Star Wars universe that are similar to one that you're looking for, so this is what the application will basically do. So it is a retrieval-augmented generation application where you'll be able to find planets which are similar to the given planet that you are searching for. So here under the hood, we are using Couchbase as our main database. So if you just want to quickly see our data, so by the way, if you're not aware, Couchbase is a really powerful distributed NoSQL database that also has support for vector store and vector search. So I have around 30 different documents where with every doc ID you can see that it contains the details about a particular planet. So we have Alderan and details such as the rotation period, orbital period, and also we store the embeddings. So these embeddings have been generated. These are of the dimension of 1500. So these have been generated with the help of OpenAI. And we already store these embeddings based on all of the data that we have stored for a particular planet. So the idea is that if a user requests for a particular planet, we are able to show them what are the set of planets which are the closest related to a particular planet. Because the way that embeddings or vector search works is that for a given vector, you find what are the set of vectors which are the closest, and these vectors represent the real world functionalities or features of a particular product. So in this case, we have the data of these planets. So if you are looking for a planet that is similar to Alderan, the vector store will be able to find those set of similar planets, and then we will use that inside of our retrieval augmented generation application where the AI model will actually respond to us. Now, we'll also actually generate an image of the planet. So based on the model of the data that we have regarding that particular planet, we'll be able to also generate an image with the help of a text-to-image generation model being powered by Nebius AI. So first, let's look at how the application actually runs, and then we'll deep dive into the functionalities and the code as well. So first, let's ask it, find planets similar to Alderan. So Alderan, if you're not already aware, it's a planet within the Star Wars universe. So now it first will perform the vector search where it will find planets which are similar to Alderan. And now you can see that it starts to generate these particular planets. So it generates the planets which are similar to Alderan, and it also generates an image of how Alderan would potentially look like. So here you can find that based on the characteristics of Alderan, it is able to find that some of the planets which are close to Alderan are Endor, Yavin 4, and it gives you the details about these particular planets as well. And it generates an image based on the description of Alderan that Alderan might look like this. Because if you carefully look at the details, so Alderan is supposed to have some mountains, grasslands, so we can probably see some of the mountains over here, and it's supposed to have a temperate climate. So based on that, we are able to generate these images. Now, the way that we are actually generating the text, so for that we are using a text-based LLM model that is powered by Nebius. Now, if you're not already aware of what Nebius AI Studio is, so it provides you a set of state-of-the-art open source models all the way from text generation with some of the most state-of-the-art models like DeepSeek V3 and R1 to also then being able to use text-to-image based models like Flux, which are some of the best models that are out there. If you have probably some vision-based models, so if you have some images and you want to describe what's happening in those images, then you can also use the vision models. There are some embedding models as well that you can actually use. So all of these are readily available to you. You can use the playground to quickly test and see the functionality of these models, and then you can use their inbuilt Python and JavaScript-based SDKs and have the API key to be able to leverage these particular models. So now let's explore the code base for our Hono.js project. The first thing that I'll quickly show you is the server.ts file. So in this TypeScript file, we are just initiating our Couchbase connection, and we have functions to connect to Couchbase, and we just try to attempt to connect to Couchbase cluster successfully. So in this case, of course, you would need things such as your connection string, username, password. Now let's go into the two main features of our Hono.js project. So the first one is the index.tsx file. So this is where all of the magic is actually happening. So here we create a new Hono app, we initialize that, and then we have a function to connect to our Couchbase cluster where we pass in our connection string, username, bucket name. And once we have initialized our connection to Couchbase, we have defined a function over here called get relevant documents. So this is where we are actually performing our vector search. So based on the input question that the user asks, for example, find planets similar to Alderan, So first, what we are doing is we are, of course, converting our input query into an embedding. And for that, we are actually using an OpenAI embedding right over here, which has been defined, where you can see that we have a client one, which uses OpenAI, and we use the text embedding ADA002 model. So what we do is that we first convert our input search query that we have put into our app into an embedding, and then we use the functionality of finding out the nearest vectors and finding out the relevant documents with the help of the Couchbase vector search. In this case, we define our index name and the embedding length. You can see, so of course, in this case, that would be around 1500 because we had generated the original set of embeddings as well for our data with the help of the OpenAI embedding model. And now what we do is that we formally instantiate a new vector search request where we pass our given input query embedding and we find the set of embeddings that most closely match. So in this case, internally what's happening is that, of course, since we are asking about a particular planet, we use the vector search to find the list of planets whose embeddings are the closest, because as we know that with vector search, the idea is that in case two embeddings are closer to each other, that means their real world features are also closer to each other. So we find the set of the nearest set of documents, in this case the planets, that are available, and then we populate that into our search results. And that is what we end up displaying and rendering over here based on the similar planets that we get based on the input query that we have given to our vector search. And the way that we are packaging all of this together is that, so we have our API chat endpoint where, first of all, when we are asking that question, as I mentioned, that we are converting that input query into an embedding. And then for the text generation, we are using the Nebius AI. In this case, the model that we are going to be using, I think, is the Llama 3 model. So you can quickly see that in place over here, because we have to, of course, specify what type of model we actually want to use. So we specify, we'll basically specify that particular model. And then what we'll do is that once we have gotten our relevant documents with the help of the vector store, this is where we have our prompt now, which says that you're a helpful AI assistant, and based on the context that we get, we will return the result of the similar types of planets that we receive from our vector store, and that is why we are using this charge completion. So in this case, we are using the Llama 3.1 70 billion parameter model, and we are generating the response. So all this model response is being generated with the help of this Meta Llama 3.1 model. And now, since we are also actually generating an image, so here you'll see that we are giving it a prompt that have a beautiful detailed illustration of that particular planet, and we use the Flux Schnell model and actually go ahead and generate the image as well. And of course, then since we are streaming this response, so we have defined our readable stream, which is getting all of this data, and then it's chunk by chunk, it is actually going ahead and rendering our output. Now, the client.tsx file is what's the front end UI. So as you might see that we have themed it around Cosmos or Star Wars. So that is why here we have just defined our simple state management for loading our values, and then of course when we are rendering the response, we are using the API chat endpoint over here, and of course in this case we also pass the user message that has been set by the user as our input request. And once we generate the response, we do the text decoding and we render that particular text. Now, of course, if our text contains the image, we'll also render that particular image. So we have just made some changes over there, and the rest of the code is pretty much just our simple chat application to render the actual chat. So I'll not go too deep into that, but yeah, that's a quick overview. And here, of course, the idea is that since this is a Hono.js project and we are going to be using the Cloudflare pages to actually deploy this, we also have the wrangler.toml file. So in this case, we are just sharing that this is a project. So of course, if you are using some of the other features of of Cloudflare, like the key value or R2 bucket for storage, or if you're using like database or using any of the AI services, you can add those and configure that inside of your wrangler.toml, because this is what is used for deploying your project with the help of Cloudflare workers. So if you're using some of these tools, the wrangler.toml file allows you to identify that, and then you can use that for deployment. In our case, we are going to be just deploying it to Cloudflare pages. So we just need the Hono.js project because we have support to deploy it with the help of workers or with the pages. So that's a great thing about using Hono.js. So that's a quick overview of this particular project, which uses a Retrieval-Augmented Generation technique, and it uses Couchbase as the vector store. And then we use, for our LLM, we are using Nebius AI Studio, and even for the image text-to-image generation, we are using the Flux Schnell model offered, which is an open source model, by the way, with the help of the Nebius AI Studio. So that's a quick overview of this particular project.